the previous lesson, you learned about the principle of working of an altimeter. In this lesson, we shall learn the practical usage and some calculations which you need to understand as an aviator. Let us recap what we learned earlier. We learned that the atmosphere is exerting pressure from top down on every object on the Earth. The molecules of air is dense at the lowermost layer, where the maximum pressure is experienced. As we go up, the pressure drops at a fairly uniform rate. The pressure also varies with temperature, which is also predictable. If we are able to measure pressure accurately, then we can derive the height at any point on the atmosphere. In fact, altimeters are refined instruments that measure pressure. Let us recap the standard atmosphere. Note that the standard temperature is 15 degrees centigrade and the pressure is 1013 hectopascals. We shall learn about these in detail. Let us understand measuring pressure. Mercury filled an evacuated tube, raised to a level which is corresponding to the pressure exerted on it in a container. The length of the column of mercury is proportional to the pressure. And by measuring the length, we could measure the pressure. The standard pressure measured 29.92 inches, which translates into 760 millimeters. Now some maths. 1 atmosphere, which is 29.92 inches of mercury, equals approximately 14.7 pounds per square inches. If you translate pounds per square inch to kilograms per meter second square, that is 1 Pascal, which is the measure of pressure on the standard international units. It approximates to 6894 pascals. Therefore, 14.7 pounds per square inches equals 101325 pascals. Or 1013.25 hectopascals. Lapse rate. It is the rate of drop in temperature with increase in height. Equals 1.98 degrees centigrade. Say 2 degree per 1,000 feet. Rate of pressure drop with height equals 27.3 feet, approximately 30 feet per hectopascal. Density correction for temperature is about 120 feet per degree centigrade. We discussed that the temperature affects the pressure. When the pressure altitude is corrected for temperature, it is termed as density altitude. All aircraft performance is directly dependent on the density altitude, and the performance graphs are drawn accordingly. Knowledge of calculating the density altitude is important for an aviator. Let us see this through an example. Altitude is 7,000 feet. Local QNH is 1003. Temperature is 5 degrees centigrade. What is the density altitude? Firstly, 1 hectopascal equals 27.3 or practically 30 feet. Since the difference is 10 hectopascals, the altitude difference is 300 feet. This has to be added to the height, since the pressure is lower. Say 7300 feet. Next step will be to find the standard temperature at 7,000 feet. We know that the lapse rate is 1.98, approximately 2 degrees centigrade per 1,000 feet. So, at 7,000 feet, the standard temperature is 1 degree centigrade. At an existing temperature of 5 degrees, the deviation is by 4 degrees. Correction for temperature is approximately 118.8, approximates to 120 feet. Once again, this correction needs to be added, since the temperature deviation is positive. The density altitude Works out to 7780 feet. I have worked another example. You may go through the process on figures critically. Now the Q codes used in altimeter setting. Quebec November Echo, QNE. This is the standard altimeter setting of 1013. Quebec November Hotel, QNH. The pressure altitude of any spot. When the altimeter is set at QNH, it reads the airport elevation or height above the MSL. Quebec Foxtrot Echo, QFE. When the altimeter is set to QFE, it reads 0, on ground, and height above the field elevation. The altimeter is set to local QNH, obtained from the ATC. Reads the correct airfield elevation. After takeoff, while climbing, the altimeter is changed over to QNE setting 1013 while crossing the transition altitude. Aircraft continues to maintain QNE setting throughout the flight. This ensures height separation between all aircraft. Aircraft height is referred to as flight level. While descending to an airport, the altimeter setting is changed to local QNH setting at the transition level. The band between the transition altitude and transition level is termed as the transition layer. Let me explain. Here, an airport is located at 1,000 feet. We have assumed the atmospheric conditions to be standard. That is, the local QNH is 1013. The altimeter is set to QNH 1013 and the altimeter will read the correct airfield elevation. The QFE setting will be 980 hectopascals and the altimeter will read 0. The transition altitude is 5,000 feet and the layer is 1,000 or 1,500 feet. In this case, the aircraft is at the airport elevation of 1,000 feet and the pressure is standard at 1013. Let us say, the next day when you came back to the aircraft, the QNH reported is 1003. The altimeter will actually be reading 300 feet higher as shown. The altimeter climbed since there is a drop in pressure. That is 30 feet for every hectopascal. Now, when you adjust the setting to the correct QNH, the altimeter will read the correct elevation of 1,000 feet. When the aircraft takes off and climbs, as it approaches the transition altitude, the altimeter setting is changed over to standard setting of 1013. Hereafter its height is referred to as flight level. A descending aircraft will change over to the local setting of 1003 at the transition level. Above the transition level, all aircraft maintain the same standard setting of 1013. Thereby, altitude separation is maintained, irrespective of type of aircraft, and places of departure, and destination. Let us take a case where the local QNH is 1,000 hectopascals. If the transition layer was at 1,000 feet, an aircraft taking off changes over to the standard setting of 1013 after reaching 5,000 feet, which is the transition altitude. The altimeter would climb by 390 feet and read 5,390 feet. Another aircraft, maintaining flight level 60 on 1013, is in proximity. The separation between these aircraft is just about 610 feet, two less. It is for this reason the transition layer is kept at 1500 feet when the QNH is less than 1013.
இதெல்லாம் explaining the maths portion of it.
Here, the transition layer is 1500 feet, but notice that the separation between aircraft is adequate at 1110 feet.
Super.
Let us take the case of a descending aircraft. The obstruction is 3,500 feet above mean sea level. A descending aircraft changes over to local QNH, which is 1,000, and its height will change to 5,610 feet. Notice that the separation is just about 2,600 feet. With a normal rate of descent of about 2,000 feet per minute, the clearance is marginal. It is for this reason the obstructions around the airfield are considered before determining the transition altitude. Also, the pilot needs to revise the sector safety altitude before commencing the descent into an airport. The methods vary from country to country. In USA, the transition altitude is kept at high figure of 18,000 feet. The pilot need to be clear on the procedures by reading the approach charts. Many countries follow the metric system, that is, elevation is read in meters. This shall be explained in the next lesson. Thank you for going through the lesson. Please offer your suggestions in comments at chandru4861@gmail.com.